Okay, welcome everyone to lecture 21. Today we are actually going to shift gears a little bit. So far in this course, in the first 20 lectures, we've discussed evaporating black holes. And in some sense, when we think of the information paradox, that is what we usually think of. You think of a black hole that's evaporating, and then you'd like to ask questions about how, what happens. Is that process unitary, and is the process of formation and evaporation unitary? And we've looked at that from different angles, and we've had many different things to say about it. But in fact, when we talk about the information paradox, we are talking about a web of interconnected puzzles about black holes. So there are some questions we can ask, which, as I've tried to explain in the course, we think we have good answers to, about how black holes evaporate and how unitarity is preserved and how information is not lost. But today I'd like to start describing a different set of puzzles that have, in some sense, a different flavor, and that have to do with large black holes in anti-de Sitter space. I'll try and explain how these puzzles have a different flavor. And then, in the next week, we'll discuss the resolution to these puzzles, proposed resolution to these puzzles. But as I'll try and emphasize, that this is the last module in some sense of what we'll talk about, as I'll try and emphasize some of the issues that pertain to large black holes in AdS are perhaps less well understood. And it's also true that in some sense, there was some activity around these issues a few years ago, but there has not been so much activity around these issues now. But in some sense, the questions that we will end up facing are interesting, and they're fundamental, and in some sense, I think they're deep. And so I think it'll be great if we could make progress on these issues. And so I'm going to try and describe this last set of puzzles about AdS. Let me just try and set up the framework. We're going to discuss large black holes in global AdS. So for the remainder of this course, we'll always be in global AdS. And today, I want to start by discussing black holes that at late times become large black holes. And that means that, the metric of the spacetime at late times becomes something like this. Where this f of r is a function that we have seen before. It has the form in AdS r square, and this mu is not quite the mass, although it's proportional to the mass, and there's some constant of proportionality that we'll never need, but we can write down once and for all. Okay, where this factor m is actually the mass. Okay, so in any case, we have some black hole solution, and we have a metric that at late times tends to this black hole solution. And the reason we write late times, and the reason I wrote late times above, is that the picture I have in mind is that if you think about this geometry, if you take the r tends to infinity limit, this geometry is always global AdS. So asymptotically, it's an AdS geometry. And the picture we have in mind is the picture of the following kind, where in the past, at some point, you created a black hole, maybe by throwing in some stuff from the boundary. So there was some black hole that was created. Here's my cartoon of some infalling matter. And then as a result of this black hole, of this infalling matter falling in, there was a horizon that was formed. And here's my horizon. But before, at early times, there was no black hole, or maybe there was a pure state. And so there is no, this is not what's called an eternal black hole. So we will actually later in this lecture itself, perhaps, or maybe the next lecture, also discuss some issues that have to do with eternal black holes. But here, this is a black hole which just lives in anti-de Sitter space, and there is only one asymptotic boundary. So this is my matter. And the whole thing, we'll imagine that the whole theory is in some pure state. Since we are going to be in AdS, everything we say right now, you can think of within the context of the AdS CFT correspondence. So you can imagine that you have a conformal field theory. The conformal field theory, you put in some pure state. Maybe earlier it was in the vacuum, then you excited the vacuum by turning on some source that created some matter. That matter collapsed to form a black hole, but of course the CFT remains in a pure state, and it's described in the bulk by this kind of a metric, which at late times tends to what is written on top. Now, we are going to be interested in the remainder of these lectures, not in asking, of course, one could ask questions about, what happens at the singularity, and that's an interesting question. But we are going to be interested in asking questions about a different part of this geometry. So we are going to be interested in asking questions about the part of the geometry which I have circled here. Okay, so if you see this circle here. And this circle includes a part of the geometry that is outside the horizon, but crucially, it also includes a part of the geometry that is inside the horizon. Okay, so this region includes some part of the interior. Okay. And also includes, of course, some part of the exterior, but of course, the puzzles that we are going to find are going to have to do with the black hole interior. But I emphasize that this region stays far away from the singularity at all times. So in this region that we are going to be interested in, we are not at any point going to have to confront like large curvatures or anything like that. We can make this black hole as big as we like, in which case curvatures in this region are always small, and we expect that effective field theory is going to hold. Okay. So this is the question that we want to ask. And how could one probe such a region? We imagine that there is some infalling observer who decides at some point to jump into the black hole, which is a very unwise thing to do, but the observer does it anyway, and jumps into the black hole. And this is the trajectory of the infalling observer. And we now want to describe the experience of this observer. And as this observer, jumps from the boundary and then crosses the horizon and in the end crashes into the singularity, we are going to be interested in the experience of the observer as the observer crosses the horizon. Okay, and that's the reason we are going to be interested in this region. We will actually not speak in terms of an observer, rather we will speak in terms, as we have done so far, in terms of observables, which are comprised of like fields or propagating fields, where we will evaluate correlators of these fields in this region, in the circular region that I've drawn. Okay. So let me first, before I say something about the paradoxes, let me just say something about the difference, a crucial difference between large AdS black holes and evaporating black holes, and why there are some puzzles that arise for large AdS black holes which do not arise for evaporating black holes. Okay. So large AdS black holes have the property that they dominate the microcanonical ensemble. And this is something that evaporating black holes never do. So when we say microcanonical ensemble, of course, it's not at low energies, but it's at high enough energies. So provided you take the energies to be big enough to form a large black hole, then these large black holes dominate the microcanonical ensemble. As a result, they never evaporate. They never evaporate. And statistically, what this means is that, let's say you take like states from a band of energies, which corresponds to large AdS black holes. So let's say you take states, and the Hilbert space, of course, is a very high dimensional space, which has some very high entropy. But, we could, let's just take some cartoon. Let's say this is our Hilbert space. And in this Hilbert space, you could shade things. So this is the volume of the Hilbert space. And the point is that almost all states, so let's say, you now go and try and pick some state from this Hilbert space, it's almost guaranteed that the state that you pick will be a large AdS black hole. Of course, that doesn't mean that all states are large AdS black holes. You see, you might have like some like very few states which are not AdS black holes. So let me draw here. So maybe, there are like some atypical states which occupy an exponentially small volume of the Hilbert space, which are not large AdS black holes. So these are atypical states. So they are not large AdS black holes. Maybe it's like a gas of gravitons with the same energy. But most of the Hilbert space comprises these large AdS black holes. So this is what happens if you just take, so this Hilbert space is like the Hilbert space which corresponds to the microcanonical ensemble. And of course, when we say ensemble, we mean taking a particular average over states of a given energy. But here, when we say Hilbert space corresponding to the microcanonical ensemble, I hope the meaning is clear. It's the meaning that we have used previously as well, where we pick a pure state from an energy band. So we pick pure states from a narrow energy band. And remember that, when you pick pure states, you don't have to pick energy eigenstates. When I say pick pure states from an energy band, you don't have to pick eigenstates. You're allowed to pick like arbitrary linear combinations of energy eigenstates. And that is what comprises the Hilbert space. And when sometimes if you say the Hilbert space corresponding to the microcanonical ensemble, that's what we are talking about. And in this Hilbert space, almost all of the volume is occupied by these large AdS black holes. And there are very few, like exponentially few states which are not large AdS black holes. Now, I want to emphasize that this is exactly the opposite of what happens with evaporating black holes. So, so far in this course, we've considered evaporating black holes in flat space. We also considered black holes in AdS just before this, which were coupled to like non-gravitating baths. But if you look at the Hilbert space of a black hole which evaporates, it is never of this kind. In fact, it's just the opposite. So if you take the same picture, so just to say, evaporating black holes never dominate the ensemble. So before I draw the picture, let me just explain why. The reason is that the reason a black hole evaporates, of course, is because the Hawking radiation that emerges from the black hole has larger entropy than the black hole itself. Okay? So the reason is that the Hawking radiation has larger entropy. And when we say it has larger entropy, it has entropy that is larger by some factor. So you can compute for a black hole in four-dimensional flat space, how much is the entropy of the Hawking radiation larger than that of the original black hole, and maybe it's like 20% larger. Okay? But the point is that 20% is still a huge number because it means that e to the s prime is much, much larger than e to the s. Okay? So when we look at evaporating black holes, they never dominate the ensemble at a fixed energy, because if you look at the Hawking radiation at the same energy, that has a large entropy. And in fact, that is the reason evaporating black holes, evaporate. It's because they have negative specific heat, and they evaporate because it's thermodynamically favored for them to evaporate. And if you were to draw the same Hilbert space that we drew before, you would find just the opposite picture. You would find that, you have some black holes. So these are like black holes. And most states are like gases. Okay? Are a gas of gravitons or photons or whatever. Okay? So the situation, and of course, by the way, this situation also happens in AdS. If you take small enough energies, then there's a regime in which you get small black holes in AdS. So this is a regime in which the cosmological scale of AdS is much longer or much larger than the Schwarzschild radius of the black hole. And in that regime, small AdS black holes behave like flat space black holes. And in that regime, it is still true that they never dominate the microcanonical ensemble. And rather, the thing that does dominate the microcanonical ensemble is just a gas of gravitons and other kinds of excitations that you can make up. And this is always true for black holes in flat space. because the volume of flat space always wins over the fact that the black hole itself has a large entropy. So notice that as a result, the picture that you have for large black holes in AdS which don't evaporate, the statistical properties are completely different. Okay? So as I said, large AdS black holes have positive specific heat, but and they don't evaporate and so on, and have different statistical properties from evaporating black holes. Okay? And the puzzles that we are going to find below have to do with these distinct statistical properties. And that's the reason we did not encounter these puzzles in our lectures so far, because we were always interested in asking questions about evaporating black holes. And evaporating black holes just do not have this property of dominating the ensemble, which large AdS black holes do. Okay? And so this is what is going to lead to puzzles. Okay. So let me now explain, are there any questions about these statistical properties? And then I'm going to explain in what sense we get paradoxes.
I have probably a bit of a naive question, but we are not looking at eternal black holes.
No, not yet. But we will, but not yet. Yeah.
Okay, but we describe these big black holes as coming from collapsing matter.
Correct.
But if I mean, the collapsing matter is then an atypical state in that sense, right?
The collapsing matter initially was an atypical state, exactly. So yeah. Initially you prepared an atypical state, which was a collapsing matter, and then it collapses, and so it thermalizes into a big black hole.
Yeah. Okay, that was my question. Yeah.
Yeah. Thanks. Exactly. Yeah. Exactly. So if you think of the dual process, it's like you have some. You take some glue balls, you crash them together in the CFT. At some point, you get some quark gluon plasma. So the large AdS black hole is indeed the process of thermalization. So most states in the world are thermalized states. The large AdS black hole is a thermalized state. But to prepare such a state, you start with some. You prepare some state by turning on a source or something, which is of course an atypical state to start with. You allow it to relax, and it forms a large AdS black hole. I mean, you don't have to think of collapsing matter. You could just say, I'm just going to somehow go and I have some process of preparing states at a given energy, and I just pick a state from that set of states. So collapsing matter is one physical way to think of how we obtain these states. But in the end, we are just going to say, we are going to pick some state at random from this band of energies. How we produced it, whether it came from collapsing matter and then evolution, or whatever else we did, that will not be important in our discussion. Okay, great. So the main takeaway of the paradoxes is going to be the following. Okay, the paradox is going to be the following. Okay, so it's going to involve a contradiction between the following two statements. The first statement is the statement that we expect, as I said at the beginning, that there is some if you look at these large black holes and you look at the region which is close to the horizon, whether in front of the horizon or behind the horizon, I said we expect that curvature scales are weak, and so we expect that the predictions of effective field theory should hold near the horizon. Maybe the predictions of effective field theory do not hold when you go close to the singularity, but we expect that if you have a large black hole, in fact, I wrote down a metric, and in general, we believe that the metric that we wrote down is valid both in front of the horizon and behind the horizon. And so we expect, so one expectation is that if you take typical pure states, which are drawn from an energy band, so energy band of large black holes means actually just the range of energies where large black holes dominate, which is basically all energies above a certain threshold, once they start getting formed and once the Hawking-Page transition happens. Okay? So if you just take typical states, we expect that, we expect that these have empty interiors. And when we say empty interiors, that means that, we expect that there's no firewall or something else of this kind at the horizon. And that's just a classical expectation. It might be that there are like some delicate effects if you measure closely or measure carefully, that change, that. So we've just written on the metric, maybe like when you think of the wave function that has some delicate effects. But we're just saying that at the classical level, if you take a typical pure state from this energy band, such a pure state should correspond to something which has an empty interior, and where we can apply the rules of effective field theory. So this is in fact the first thing I started saying, and it seems to be such a natural assumption that it hardly, it hardly merits making explicit, but it is going to be something that's going to, that is going to run into trouble. So this is one assumption, okay, and it seems like a very reasonable assumption. And the second assumption is going to be that the degrees of freedom in the black hole interior are described by the same operators in all microstates. Now, of course, for those of you who are familiar with the story, this is the assumption that we will start discussing in some more detail from next time. But at first sight, this seems like a pretty innocuous kind of assumption, because this is how we usually do quantum mechanics. We say that we have some system, and in the system we have a separation between the observer and what is being observed, and the observer picks some basis of Hermitian observables to use, and that basis is just fixed once and for all. And then you prepare a state, and then in that state you can measure like some Hermitian observables that you picked in the first place. But in general, we don't vary the observables based on what state we have. And so this also seems like an innocuous assumption. But later, this assumption, the second assumption, is what we're going to explore at length, and we're going to see what happens if we relax this assumption. But for now, we are just going to make these two assumptions, and we'll see how very quickly we run into trouble and we end up with a contradiction. Okay, so let me first remind you about what point one here means. Okay, so I said rules of effective field theory, but what does rules of effective field theory mean? So in fact, rules of effective field theory means basically the rules that we explored in the first few lectures of this course. It means the fact that if you take some propagating field, which for simplicity we can take to be a scalar field, and it propagates in the vicinity of the horizon, then the short distance behavior of the field is just given by the geodesic distance. And that's just because we expect that curvature scales are large. And so if you go to short enough distances, the space looks approximately like flat space. And so that's something that we explored at significant length. And so when we say the rules of effective field theory, all we really mean is that let's consider some bulk scalar field. Scalar field is just for simplicity. You could take a field of non-trivial spin. Let's consider a bulk scalar field. And then the rule we want is only that by smearing the field, we can get some modes which we will call A omega outside the horizon, and some modes which we will call A tilde omega, which you get by smearing the field behind the horizon. So these modes are precisely defined in the sense that we described in the first few lectures of this course. You take the field, you integrate it with some u to the I omega or minus u to the minus I omega, and you also actually need to integrate it with some spherical harmonic. So there should have been an L index here, and in fact, if you look at the lecture notes on the archive, there is an L index there. But I'm not going to write the L index because it will never be important for anything we do. If you were to consider black holes which have angular momentum, it would be important, but for simplicity, we won't consider them. And so we're just labeling the mode by its frequency. And there are these modes out that you get by taking the field, integrating it with some smearing function outside the horizon, and some modes that you get by taking the field and integrating it behind the horizon. And we have seen these modes several times in the course. And there's some rules we had, some 2-point correlators that we derived for these modes. And the rule was that we must have the following rules. Let me just. So if you have like a state which corresponds to something which has a smooth horizon, then we have the following correlators. So this is one correlator, which is a 2-point function for a. Sorry, did I mess up my? No, that's fine. I think, yeah. So this is one correlator, which is a 2-point function, and then these modes, as we have written them, happen to be canonically normalized. So remember, we smeared these functions. So instead of delta function normalization, we have a 1. You could think of modes which have delta function normalization, but it'll be convenient here to think of modes which are normalized with a 1. And this a omega tilde also has the property that it commutes with itself. And a omega tilde commute with each other. And there is also a cross correlator between a omega tilde and a omega. And that cross correlator is of this form. Okay, so these are what we are calling the rules of effective field theory. Okay, and as I said, all this follows just from the 2-point function of the field. So all we are saying, we are making like, it seems like a very reasonable demand, which is that everything follows from the 2-point function of the field across the horizon. So we are only saying that the horizon should locally look like, it should locally look like flat space. And that's all we're asking for. And you might have thought, what's the puzzle here? There's nothing even evaporating. So, we had this monogamy paradox that we discussed, but there's no monogamy paradox here because the black hole doesn't even evaporate. So there's no notion of an old black hole. And you might have wondered, why there should be an issue about this at all. And I'll now explain why there's an issue. Let me first remind you also of 2 other commutators that we derived earlier, but perhaps we did not emphasize. And those 2 commutators have to do with how these modes, a omega and a omega tilde, behave when you commute them with the Hamiltonian. Okay? So the commutator is that H a omega is minus omega a omega. So a omega has negative energy, so it tends to draw out some energy. And we have that H a omega tilde is plus omega a omega. Okay? So the way these commutators come about, let me just remind you, is that if you take the field and you write it as phi t r omega, and if e to the iht generates for you like time translations of this field, if this is what takes you to phi of t plus tau r omega, then this is sufficient to give rise to these commutators above. And these commutators only arise because if you go back and you look at the field expansion that we wrote down at some point across the horizon, you will find that the field expansion had the form a omega into e to the minus I omega t plus dot 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 outside the horizon. So phi had this form, and inside the horizon, it has the form a omega tilde into e to the plus I omega t, and there were other terms. But the important point is this point, okay? Is the fact that you have reversed the sign here. And if it is then true that e to the ih tau, just shifts phi from t to t plus tau, then it follows that the commutator of h with a tilde will be the same as as what is written here, and the commutator of h with a will be minus of omega a omega. Okay? There's a more formal way of saying this. And the formal way of saying this is that you can gauge fix this operator. And the way you would like to gauge fix this operator is that we have this black hole, we have a horizon, and the way this operator is gauge fixed is that when we talk about this operator, we start from some point on the boundary, like here, and then follow a geodesic in the bulk. So this is what we would call a gravitational Wilson line that we discussed a few times in the course. And you follow a geodesic in the bulk for a certain length, and at the end of that geodesic, you measure the value of the field. And that gives you, maybe not an extremely precise notion, because you might worry about what happens, if the metric is fluctuating, but it gives you a good notion, at least to leading order, of what this field that you're talking about is. And now if you act with e to the IH tau, this e to the IH tau, what it does is it translates the entire trajectory, the starting point on the boundary, and just translates everything. Okay, so this is e to the IH tau, translates the entire configuration. And notice that, the configuration was translated outside the boundary, but because we are thinking of a geodesic, and because this metric at late times develops like a killing isometry, it is t that gets modified inside as well. Remember that inside the black hole, t is actually not the time coordinate, it is r which functions as the time coordinate. And so you might be puzzled about how it is that e to the IHT is still generating translations of t. And the reason it's still generating translations of t is because of this. It's because of the fact that e to the IHT really generates translations of t on the boundary. And if you define the operator in the way that I just described, by dropping some geodesic in the bulk and following it to its end, then if you do e to the IHT, the entire configuration gets translated by some amount, and that generates really translations of the coordinate t inside, even though it's not the time coordinate. Okay. So in any case, the end of the story is that we have these commutators, and these commutators are going to be important. Okay, great. So far, I've just said something about what we meant by the rules of effective field theory. Let me now come to the paradoxes.
Sorry, can I ask a question?
Yes, sure.
What is the assumption here? So in this second part, are we making any assumption on rules that we assume being valid?
Here, this assumption, this follows from how phi was gauge fixed. Follows from the definition of phi. I mean, when I say definition of phi, I mean in terms of how it is gauge fixed. You see, when we talk about a local operator in gravity, we have to decide how we are going to dress the local operator. And if we decide to dress it by dressing it to the asymptotic boundary, then which is basically the only thing you can do. You have to dress operators to the boundary. And if you dress the operator in this way, then which is the natural way to dress it, then this is what this is where these commutators would come from. Okay, so if you take a gauge fixed operator and you work out what the point is that the commutators with the Hamiltonian are a little bit subtle, because they depend on how you gauge fix the operator. And this will be a little bit more important when we discuss also eternal black holes, because there we will have a choice of whether to dress the operator to the right boundary or to the left boundary. And depending on how we do that, there are different commutators you could get. But in the case of the single-sided black hole, there's really only one choice. And if you dress operators to the right boundary, then you do a time translation. It shifts the points where you dress the operator to on the right boundary. And so it must also shift t inside. You could try and define some operator in some totally different way that would not have these commutators, but that would be, it would not correspond also to what we usually think of as what's happening to an infalling observer. An infalling observer is kind of falling in, and then you're trying to ask, what does the observer see after a certain amount of time? And that's why this is a natural gauge fixing. Does that answer the question?
Yes, it does. Thank you.
Great. Okay, so here is a paradox which we can call the negative occupancy paradox. Okay. So, I said that it's actually just going to follow from the rules that I just wrote down. Okay. So I said that, we want that the modes inside should be thermally occupied. By the way, let me just point out that these rules that we wrote, these ones that we are now going to use again, are just telling you that the whole system is at a temperature, at an inverse temperature beta. Okay? So this is just telling you that if you look at the occupancy of these particles outside, they are occupied as if they are at an inverse temperature beta, at temperature 1 over beta. Right? And that's natural, right? Because this is the occupancy of some scalar field. The whole system, the black hole acts like a huge heat bath. So the whole system is really at some temperature, which is 1 over beta. And so these correlators are really natural correlators, right? They're just like, they literally are correlators that are measuring like the occupancy of the field outside, and that is at some temperature, which is 1 over beta. And they're also measuring the, that's also true of particles inside the horizon. So everything is occupied at some inverse temperature, which is 1 over beta, or inverse temperature, which is beta. Okay. So here is the same correlator that I wrote. And let me also copy one more thing, which is this. Okay, great. So now I said that we have these typical pure states, and this expectation that I wrote here was something in a typical pure state. But really, we proved that typical pure states were close to the trace in the microcanonical ensemble, and we know by the equivalence of ensembles that the trace in the microcanonical ensemble is close to the trace in the canonical ensemble. And therefore, if you're measuring the correlator of any operator in a typical pure state, you can also compute what you expect by just computing the expectation value in the canonical ensemble. In fact, what we proved was that it's the same as the expectation value in the microcanonical ensemble. And when you go from the canonical to the microcanonical ensemble, you'll get some powers of 1 over square root s. But we are not bothered about those powers of 1 over s or power law corrections in s. Everything we say is just going to be about order 1 terms. And at order 1, you can just replace an expectation value in a typical pure state with a trace in the canonical ensemble. And therefore, if you believe the first line that we have here, then it tells you that trace of e to the minus beta h of a omega tilde dagger is equal to 1 by 1 minus e to the minus beta omega, right? Okay, let's call this object T. Okay. And now I'm just going to play some games with T, and we will see how we are very quickly going to run into trouble. Okay, so the first thing is, you know that the trace is cyclic, right? We know that the trace is always a cyclic object, and so you should be able to trace, move things around in the trace, and therefore this T is actually equal to 1 over z beta into the trace into the a. You move the a omega tilde dagger to the left. So I didn't do, this is just using the cyclicity of the trace. Okay, so I had a trace and I said, I know something about traces. I was taught in high school that traces are cyclic, and so I can move things around. And so I moved the trace from the front to the back. I moved this person from here to here. Okay, great. So now I also know how this commutes with the Hamiltonian. In fact, I've been writing down the commutator for a omega tilde, but there's obviously the opposite commutator for a omega tilde dagger. And I have here e to the minus beta h, and I have a omega tilde dagger. But remember, a omega tilde dagger reduces the energy. Okay? So if I'm going to act with e to the minus beta h, and I want to move the a omega tilde dagger here, I need to add a compensating factor of e to the minus beta omega. And I need to add a factor of e to the minus beta omega. Okay. This comes from commutator with h. So this is the second step. and I hope you're all following. If you're not following, please stop me. In the first step, I had the definition. In the first step, I used the cyclicity of the trace. In the second step, I used the commutator with the Hamiltonian. And so I now have this expression for what I started with. But now I also have the commutator of A omega dagger with A omega tilde. Right? I know I can write A omega dagger with A omega tilde as A omega tilde. I can interchange the order of these two at the cost of a 1. Right? So this is in fact the same as trace of e to the minus beta h into A omega tilde dagger minus 1. Right? Into e to the minus beta omega. So if I have the A omega tilde dagger up front, that gives you a larger number, and therefore, I should write this as A omega tilde into A omega tilde dagger minus 1. So this is the commutator with itself between the two. Okay. But now look what we have here. This term is just e to the minus. So we have here e to the minus beta omega. And this term is just 1 because you have a minus 1, you have trace of e to the minus beta h, and you have here the partition function. So this whole thing is just going to give you an e to the minus beta omega. And this is actually what we started with up here. Right? So we have found that t is equal to e to the minus beta omega into t minus 1. Or minus e to the minus beta omega. Okay. And that gives us the wonderful result, which is that t is minus e to the minus beta omega by 1 minus e to the minus beta omega. Okay. Okay. The reason I write the question marks is because you see you have got a negative result for an operator, for the trace of an operator that is manifestly positive. Okay. So we are taking the thermal trace of an operator which is clearly positive. It's something multiplied by its conjugate. You're taking the thermal trace, but so what? You should get something which is 1 or something, something which is larger than 0. And here we got a negative answer. In fact, the answer we were supposed to get was 1 by 1 minus e to the minus beta omega. Not only did we not get that, we got this factor of minus e to the minus beta omega. And it's worse than just being a factor that's wrong. It's actually, just totally wrong. It's just a result that doesn't make any sense. Okay. So we see that we have got an absurd result just by putting together the rules that we had from effective field theory. So, we just put together some standard rules from effective field theory, and we ended up with this paradox. Okay. Okay. So what does this paradox actually tell us? What does this calculation actually tell us? Okay, it tells us that, if we look for like some fixed operators, it tells us, and at least historically, what this paradox, it wasn't quite this paradox, but I'm presenting is a simplified version of some of the paradoxes that were discussed some years ago. But what this paradox suggests is that if we look for a fixed A omega, as I said, that has the correct properties in typical states, it does not exist. So this is what the paradox is suggesting. On the other hand, note the paradox does not rule out the existence of such operators which have the right properties in a set of atypical states. Okay. For a small set of states. So small here can even be power law small, okay, or can be exponentially small. So it could be that there are some states which correspond where you can find these operators, and this paradox does not rule it out, because remember the paradox has to do with the trace. And if in this trace there are some the paradox is telling you that such operators which have these right properties do not exist, And in fact, you can't find an operator which has the wrong commutator with the Hamiltonian, but yet its occupancy is this. But on the other hand, it doesn't tell you that there can be no states in which this operator doesn't have this expectation value. So it could be that for some states, this A omega tilde behaves correctly. But what this paradox is telling you is that if you just fix some operator and you take a trace, it can't be that it behaves correctly all throughout the ensemble. Okay, and that's pretty important. And that's why these paradoxes never arose when we considered in the first part, in most of this course, evaporating black holes. And that's because evaporating black holes, as I emphasized earlier, are atypical states. And so, this paradox doesn't rule out the existence of these modes for a set of atypical states. Okay. And what this paradox was used to argue for historically was used to argue that either large black holes in AdS have firewalls, or at least AdS CFT or the boundary theory does not describe the interior of such black holes. So you somehow need to supplement it with some degrees of freedom before it can describe the interior of large black holes. Or if you decide we just want to take AdS CFT as it stands, then this paradox was used to argue that large black holes in AdS have firewalls. And I want to emphasize that in this, let me just write in a box, we had all these resolutions. We've talked about all sorts of resolutions. We talked about the holography of information, but it does not save us here. Okay. And neither, do islands or anything else that we talked about. So, we talked about how, the Hilbert space may not factorize and how you may need to identify degrees of freedom far away and degrees of freedom inside the black hole. So we talked about, how there's this redundancy in description, which is the holography of information, but, that doesn't matter. You can have that. You can have, you can say whatever you like about what these operators A omega tilde are. You can say that maybe A omega tilde and A omega, we said here, they commute. Yes. Yeah, I said here they commute. So you could say, we don't want them to commute. We want them to have like some non-zero commutator, which is exponentially suppressed or whatever. But whatever you do, we didn't use that commutator. And so it's pretty important that these other things that we discussed here are not going to resolve this paradox that we have for negative occupancy. Okay. So this is what this is. I'll now give you another example of a paradox which has the same flavor. But this paradox already captures, there's some set of paradoxes, all of which are similar, which one can construct, but this paradox already captures the main points. Okay. So this was what this paradox was historically used to argue for. And this, in some sense, is a much more formidable argument than the argument that was given for firewalls using the monogamy paradox. So for the monogamy paradox, we saw, there is a resolution where you use the holography of information. And then in other contexts, we discussed how, if you have like some black holes which are coupled to non-gravitating baths, there might be islands and so on. But this paradox that we have here doesn't even involve any such evaporation. It's just saying, just find me the right operators that describe the interior for large black holes, and we are finding that we can't find such operators. Okay. So before I go on to the next paradox, which has very much the same flavor, maybe I can ask if there are questions about this part. Okay.
Sorry, about one question. Yeah. Because if we would couple this black hole to a heat bath at some time
yes,
then it would evaporate, right?
If you coupled it to something which you mean to some bath at a lower temperature, to something which has infinite number of, yeah, then it would evaporate. Yeah. Yes.
Yeah, but in that case, then the island proposals should yield the same answer, right?
Yeah, it would evaporate, but of course it would be true that first of all, as I said, the island proposal is so let me say a few things. So you're right that it would evaporate, but of course it would be true that in this big system, which is the black hole and the bath, the black hole would now be a very atypical state. So if you were to say that these operators A omega tilde are somehow drawn from the bath, or they're drawn from this, you now have a much bigger space of operators that you can find. And this trace of e to the minus beta h that you're now going to take is not going to be a trace of e to the minus beta h over the combined system of the bath and the black hole. So when you couple the black hole to a bath, you turn it in some sense from a typical to an atypical state. That's one thing. The second thing is actually, as we discussed, in some sense, this computation of the page curve will go through whether or not you have a firewall behind the horizon, because the computation of the page curve, it has to go through, or it has to go through because the computation of the page curve really involves taking one system, which is this CFT at a given temperature, and coupling it to another system. So you really have two non-gravitational systems. And if you did have a firewall, and there are some states, for which the CFT does have a firewall, so you can construct a firewall by like putting some shock wave or not having an interior, you would still get the page curve. So the page curve is, because you just always get the page curve. So the page curve is almost guaranteed. And the fact that you get some page curve by taking this system and coupling it to another non-gravitational system cannot really tell you much about the interior. It can't really be used to say much about the interior. Now you might say that we had these Ryudakinagi surfaces, and maybe some of them explode the interior, and that gives us some evidence, but none of that really resolves this paradox, because it could be that those calculations work for like atypical states where you have a smooth interior, and maybe they you can't use those calculations in this form for these typical states. And for these typical states, you have a firewall, but you still have the page curve, because the page curve really is not probing what's happening in the interior of the black hole. It's not even probing. I mean, it's as we discussed many times, it's just basically probing transfer from the CFT to the bath. So the island proposal can't really say much about the interior. And neither can these other we discussed this notion of complementarity or holography of information. We said, you write the interior degrees of freedom as scrambled versions of degrees of freedom far away. But that by itself, can't tell you that you have a smooth interior. It could be that you have a firewall, and there would be, So really, one has to address this proposal this paradox in a more direct way, in that one has to somehow find such operators A omega tilde, the resolutions we had for evaporating black holes, which were important to argue that the whole process is unitary and you don't lose information, are not enough to tell you that you don't have structure at the horizon of this kind for large AdS black holes. I don't know if that answers the question.
Yeah, it does very much. Thank you.
Great. Fine. Okay, great. So let me now give you another example of a paradox of this kind. The second paradox has a similar flavor. It was first constructed by Marolf and Polchinski, and it involves the infalling number operator. Okay, so what is this paradox? So it's going to be very similar. So let's consider the following operator. Okay. So we consider the operator, which is, I'm writing down some combination. It'll be clear in a minute why I'm writing down some combination, why I'm writing down this combination. Okay, so I have some combination of ordinary and tilde operators. Okay, now this operator, I'm calling it the infalling number operator, but in particular, you can check that for states which have a smooth horizon, we have the property Now, why is this the case? It actually follows from what we said earlier about how these A omega and A omega dagger operators act. For instance, let me remind you that we pointed out that for states, just by using these properties of these 2-point functions, at some point we derived this property that for such states, you had this property between these A omega tildes and A omega daggers. And so you see, if you look at this combination here, this A omega tilde minus e to the minus beta omega by 2 into A omega dagger, this just annihilates the state. Same for this combination. Okay? And therefore, you can see that the expectation value of this operator is 0. The reason I'm calling it the infalling number operator is because if you go back to Birrell and Davies and you ask, this is the operator that tells you the transformation from the so-called Rindler modes to the Unruh modes. So this operator you can think of as what an infalling observer would detect if the infalling observer was carrying some kind of Unruh detector. But if you don't want to think of that, we just have some expression. This expression in the end is just a bilinear in some scalar field. Remember, because all of these are just some smeared versions of the scalar field. So we have here some operator which is a bilinear in the scalar field. And it's just manifestly true that by what we were calling the rules of effective field theory, the expectation value of this operator is 0 for states with a smooth horizon. Okay. So now this is something that we expect. This is one of the rules of effective field theory. We expect that if you have an empty interior, then the expectation value of this operator should be 0. Now let's consider a different operator. So consider the Schwarzschild number operator. Okay, so this is a different operator. This operator is just counting the occupancy of the modes outside. Okay, so it's just counting the occupancy of the modes outside at a given frequency. Okay, so this is it's not, you can think, if you're thinking in Rindler and Minkowski terms, this is just like some Rindler number operator. And let's define some eigenstates which have the property. So when I write n, I mean these are some eigenstates of the Schwarzschild number operator. Now notice that in such an eigenstate, which is an eigenstate of the Schwarzschild number operator, the correlators of A omega and A omega tilde are quite different. And in particular, notice that A omega tilde is equal to 0. And the reason for this is that notice that this number operator, because of what we said about the commutator, or at least provided the commutator between ordinary operators and these tilde operators is 0 to a good approximation, we see that this state is still an eigenstate of the number operator with the same eigenvalue, and so clearly it is orthogonal to A omega dagger n, right? Because this has one higher occupancy. And therefore, if I look at this 2-point function, like this 2-point function, that is clearly 0. So this 2-point function is 0. And so these Schwarzschild number eigenstates do not have the right correlators that we expect between A omega and A omega tilde. Okay? And so in particular, these Schwarzschild number eigenstates, these states which satisfy which are eigenstates of the Schwarzschild number operator, cannot be the right operators to have a smooth or an empty, or have a smooth horizon or have an empty interior. So such states exist, but they don't have the right fluctuations. Remember, to have a smooth interior, you shouldn't be in a number eigenstate of the Schwarzschild number operator. Rather, you should have some fluctuations in the number operator, and on the mean, you should have the right thermal occupancy. But if you really pick an eigenstate of the number operator outside, it doesn't have the right correlators. It cannot have the right correlators between operators in front and behind the horizon. And so in particular, such a state does not correspond to a smooth horizon. Okay, so fine, we could say that's fine. Such a state corresponds to a firewall, but maybe these states are very atypical states. They're not typical states. And so, fine. So there are some firewall states, and these firewall states, are the ones which are eigenstates of the number operator. Okay, but now we are going to run into a paradox in the following way. Okay, so in what I just said, actually, we can make a little bit more precise. by just computing the expectation value of this infalling number operator in one of these Schwarzschild eigenstates. Let me take this this expression and just show you something about that. Okay, let's forget about this 1 minus e to the minus beta omega. Let's put an n here and an n here. Okay. You might have to squint a little bit at the screen, but just notice that there are various expressions here, and we can very quickly put a bound on what this expression has to be. Notice here we have an expression. If you just we have some terms which are cross terms, which are a omega dagger times a omega. So that could be 0. It's a positive operator, but could be 0. But notice you have this a omega tilde times a omega, which we said was 0 when you sandwich it inside an n, right? And then we have similarly cross terms here, but we also have some terms which look like a omega tilde times an a omega tilde dagger, and this is multiplied with a factor of e to the minus beta omega. And here we have again an a omega tilde dagger times an a omega tilde, which is a positive operator, but could be 0. And here we have an a omega times an a omega dagger, which is always larger than 1, and is again multiplied with an e to the minus beta omega. So this is always greater than twice of e to the minus beta omega. Okay. So you see that the expectation value of this infalling number operator in this Schwarzschild eigenstate is not 0, and in fact it's bounded below by this term. Okay. And that's what we just said. It comes from the fact that the omega tildes and the omegas don't have the right correlators, and therefore you have this number operator is non-zero, and that's what's telling you that you don't have a smooth horizon. As this infalling observer falls in, the infalling observer expects to see some particles at the horizon. Okay. But now notice something. Notice the following. Notice that h times n omega, this is the Schwarzschild number operator, okay, not the infalling number operator, that this is equal to 0. Okay. Plus small corrections, but we don't care about those. Why is it equal to 0? Because h times, remember, we're just computing h times a omega dagger. Okay. And you see h has the opposite commutators with a omega and a omega dagger. And therefore, h times n omega is 0. These operators are smeared a little bit, and maybe there are small corrections and so on. But up to these small corrections, the number operator commutes with the Hamiltonian of the full theory. Okay. But now let us compute the trace of the infalling number operator in this energy band. Okay, so let's compute the trace, or the sum over E, where this E is in some energy band. Okay. And this, of course, we proved is equal to the expectation value of the number operator in a typical state, and therefore we expect that this trace should be 0. Okay. Let me just show you how these things lead to a contradiction. Let me take these 4 and copy them. Next page. Okay. So the contradiction is that when you have a trace, what we are tracing over is energy eigenstates. But because energy eigenstates are eigenstates of H, and because the number operator commutes with H, you can do a change of basis in the trace. When you have two operators and they commute with each other, you can rewrite the eigenstates of one in terms of the eigenstates of the other. In general, you expect that the eigenstates of one, maybe the way we pick this basis involves it means that when we write in terms of n, we have to pick various linear combinations of all sorts of n operators. And so for any given eigenstate, you can't say so much. But because you can perform this change of basis, it tells you that this the sum over this energy eigenstates of Na can be replaced with a sum over the number eigenstates. So this involves a change of basis in the trace. But now you see you have a contradiction, because we just derived here, even though I made it small, that the expectation value of this Na in one of these number eigenstates was bounded below. And so from the right hand side, we see, let me divide by 1 over e to the s so that I get some bounded value. You see that the right hand side is larger than or equal to this quantity, whereas what we wanted was 0. Okay. And so we have found that, we expected that if typical states were had empty horizons and we wanted 0, but if this is supposed to be 0, if the trace, if in typical states the expectation value of the number operator is supposed to be 0, which is where this left hand side came from, then you do a change of basis in the trace and you find 0 is equal to twice e to the minus beta omega by 1 minus e to the minus beta omega, and that is clearly not correct. Okay. So we see that we have run into another contradiction once again by just applying the rules of effective field theory. And once again, this contradiction involves these operators a omega tilde, and we are once again finding that you cannot find operators which obey the right rules of effective field theory if you then also demand that they obey the same operators work in all states. So this is the second paradox of this kind. You can in fact go ahead and construct more such paradoxes, but they don't teach us anything new. But it's pretty important that all these paradoxes involve a trace. Okay. So all these paradoxes involve some kind of a trace. So they are always paradoxes about typical states, as I said at the beginning, and that's why they don't apply to atypical states. They may not apply to black holes in our world, but if you want to understand whether AdS CFT works correctly for large AdS black holes, these paradoxes are important. Okay. So now this is what I wanted to say about this. And as I said, once again, let me just repeat something I said. This does not rule out the possibility that a small fraction of states so sometimes people say we formed black holes from collapse, and we see that when you form a black hole from collapse, the horizon is empty and there are no large effects and there's no formation of firewall. But in fact, as we were discussing also earlier in this lecture, when you form a black hole from the collapse and you think of a classical process that's forming the black hole, you're thinking of a very atypical state. And, so you have a very atypical state, and these paradoxes do not rule out the possibility that in such a state, at least at early times, you find that you have a smooth horizon. To get to a typical state, you would either have to take a black hole formed from collapse and then wait for a long time. You perturb it in all possible ways, you allow time evolution, and then it would start approaching some kind of a typical state. So you would either have to wait for a long time, or you'd have to have some other process of black hole formation. So the fact that these paradoxes do not rule out the possibility that a small fraction of states can have empty horizons is important, because they tell you that these arguments that we have just from classical physics saying, look, we formed a black hole from the collapse of matter and it doesn't have a firewall, are not enough to rule out the fact that for typical states, you might still have a firewall. Okay, so that's the significance of this part, and this also applied to the previous paradox that we have about negative occupancy. Okay, great. So far so good. I now want to emphasize something about eternal black holes. So I'm going to change gears a little bit and talk about eternal black holes. But if there are any questions about this part, I can take them now. Okay. If there are no questions, it worries me a little bit because it means maybe I was not clear, but you should go and think about these paradoxes. I think these paradoxes are really simple. And sometimes, as I said, they're not considered sufficiently in the recent literature. There have been many things that we've learned recently about the information paradox, but they don't really touch on these problems. So I think these paradoxes in some sense are very interesting. And they're also very simple to construct, as I've shown you. Please think about it and we can discuss this more. But let me now shift gears and say something slightly different. Okay? So sometimes people say, these paradoxes. So sometimes people might say the following. And these paradoxes have to do with pure states. Or have to do with with single-sided black holes. But we don't want to consider single-sided black holes. Okay, let's consider, somebody might say, we want to consider eternal black holes. Okay, so I now want to point out that the same paradoxes, and this is actually an important point, and I think it's not widely appreciated, but as I'll show you now, it is true. The same paradoxes also afflict the eternal black hole. So, if it is true that, as I said, we'll discuss some resolutions to these paradoxes. But if it is true that single-sided black holes have firewalls, then the same arguments would lead you to conclude that the eternal black hole already also has a firewall. So, it's not, I think there's a common opinion, or some, at least in some sections, there's an opinion which says, look, we have these paradoxes for single-sided black holes, and let's not think about single-sided black holes. That's too complicated. Let's only think about the eternal black hole. But in fact, the same paradoxes continue for the eternal black hole. Of course, you don't have to come face to face with it. There are many computations one can do in the eternal black hole where you don't have to face these paradoxes. But that's also true of the single-sided black hole, right? We had, we understood, or we were studying AdS black holes for many years. These paradoxes were understood between 2012 to maybe 2015. And there are many calculations people did with single-sided black holes where they didn't come face to face with these paradoxes. And that's also true with the eternal black hole. There are many calculations one can do. But the point is, if one thinks carefully enough about the eternal black hole, one will find that the same paradoxes that I've shown you right now for the large single-sided black hole also appear there. And so, these are not paradoxes that can be somehow brushed under the rug by saying, we don't care about single-sided black holes and let's just work in things we understand. Even this system, which we think we understand very well, has these paradoxes. Okay. So let me start by just reminding you, perhaps there's some people who may not be familiar also with the eternal black hole. So let me just start by reminding you about the eternal black hole. And we'll actually come to the paradox in the next lecture, but let me just remind you of some basics of the eternal black hole. Okay, so the eternal black hole is the same geometry that we described, except I'm now not going to put t to the infinity. It really is just this metric. It's this metric for all times, where this f of r is what I wrote previously. And there's no t to the infinity. Okay? So notice here, there's no t to the infinity. Okay? So it's not that this black hole was formed from a collapse. This black hole just always existed. Maybe there was some process that formed this, but for all we know, in some sense, this state that we're looking at, whatever formed it, the trace of whatever formed it is gone, and now this black hole just exists forever. And so this geometry looks like the following. It might look deceptively similar, but in fact, it's quite different in some important ways. The geometry looks like this. And this geometry has two boundaries. So this is the right asymptotic boundary. And this is the left asymptotic boundary. And of course, to get to this geometry, you have to take the metric that I wrote above, and you have to perform its maximal Kruskal extension. And if you do that, you will find the second asymptotic region. So you will find, first when you extend it, you can extend it across the horizon, and then you will find another horizon, and then you extend it, and you will find another asymptotic region. And similarly, you could extend it this way, and you would find the same asymptotic region. And so this geometry is different in that it has two asymptotically AdS regions. Okay. And this is the right future horizon. This geometry also has a past horizon. So it has a right past horizon. And similarly, on the left, there's a horizon here and a horizon here. So these are the left horizons. Okay, so this geometry has not only a future horizon. If you go sufficiently far back in the past, there's another horizon, and there are these two asymptotic regions. And so, as I said sometime earlier, the fact that there are two asymptotic regions will create some additional subtleties that we will deal with when we come to them. But it is believed that this kind of black hole is dual to what's called a thermofield double state on the boundary. And the thermofield double state means the following. It means that you take a state, if this black hole was described by some CFT, you take two copies of the CFT and you entangle them together in the way that is shown here with an e to the minus beta e by 2, and then with energy eigenstate being entangled with energy eigenstate. And there's some normalization factor, but then you sum overall energy eigenstates. And it's believed that this kind of an eternal black hole is dual to this kind of a thermofield double state. Okay, and there are many checks of this proposal, and we think we understand this proposal well. But as I'll show you, there are some paradoxes, and I want to emphasize that there's a lot of discussion about ER equals EPR, but really the one example where we really understand what ER equals EPR is, and this is the canonical example of ER equals EPR, is this setup. Okay, so when we talk about ER equals EPR, this is the canonical example of ER equals EPR. Okay. Why is this an example of ER equals EPR? It's because this wormhole is the Einstein-Rosen bridge. Okay. So there's a wormhole here. And on the boundary, you see an entangled state. Okay. You see a state of two CFTs which is entangled, although it's non-interacting. So these two CFTs, maybe at some point in the past they interacted, but it's important that now they're non-interacting, and you now have a non-interacting state of these two CFTs. So the two CFTs are entangled but non-interacting. Let me point out a curious feature of the eternal black hole setup, which actually is very curious in some ways. It's something that again is perhaps not emphasized enough. Usually when we have a setup when you have two CFTs which are entangled but non-interacting, usually this means that no unitary on one system can affect the other system, right? So that's what we usually say, and that's true here as well. I mean, it's true here as well, right? If these two CFTs are entangled but they're non-interacting, and of course, maybe I shouldn't write usually. This is true, for entangled systems, and it's true here as well, right? Entangled systems. Usually if they're non-interacting, this means that entangled but non-interacting, it means that no unitary you do on one side can affect anything on the other side, and that's true of the EPR pairs that we have, right? You make a unitary on one side, and that's also true on the CFT. Now, if you're just making CFT observations, you take you do some unitary and it can't affect what happens to the right CFT if you do something on the left CFT. On the other hand, think of the bulk. Think of what's happening in the bulk. So in the bulk, think of some observer who was produced from this side. So we have an observer who's produced at some point from the right CFT. So an observer from the right CFT. And this observer from the right CFT jumps into the horizon as the observer was doing in the previous for the single-sided black hole and crashes into the singularity. But now notice that if from the left CFT you send a shock wave, so this is a shock wave sent from the left, then the observer will interact with this shock wave. Okay? So even though this observer was living in some system or was produced from a system in the right CFT, which we believe is entangled but non-interacting with the left CFT. So you would have thought, you produce some observer in the CFT and you send the observer into the horizon, and there's nothing you can do in the left CFT that can affect the observer. But actually that's not true, because behind the horizon, the observer is affected by a shock wave that comes in from the left. Okay? So at least that's what the proposal tells you. And notice that the shock wave can never cross the horizon. So you can't do something in the left CFT that will affect something directly in the right CFT. I mean, you can if you turn on interactions between the two CFTs, but we're not doing that right now. And so as it stands, you can't send a message from the left CFT to the right CFT, but you can have two observers, one from the left, one from the right, who jump in and they meet inside the horizon. And that's actually a very curious fact from the way we usually think of entangled but non-interacting systems, where we think that, no unitary, so this shock wave could be produced by unitary, where we think that, no unitary acting on the left can affect the other system. And that's true here, except that, when you think of the bulk, the situation is more complicated. These unitaries can interact in the bulk, and the experience of the observer from the right is affected by whether or not the observer from the left acted with a shock wave. Okay. So in any case, this is a property, and we'll now go on and say a little bit more about the paradoxes that we get. So let me just, since we are running a little short of time, let me just write down what the paradox is. Actually, I'm doing pretty good. Yeah. So the paradox is going to involve the. Yeah. So is there a question?
Yeah. Because I thought in the eternal black hole case that the entanglement of the CFT was defined at the t equals 0 slice. Right. So how does, because if we want a shock wave to interact with an observer coming from the right CFT, then we have to move beyond the t equals 0 slice, right?
So let's think in the Heisenberg picture. So in the Heisenberg picture, there's just some state. I mean, we can either think in the Schrodinger or the Heisenberg picture. In the Schrodinger picture, the state is just this state. So this is just the state of the whole system, like this thermofield double state. You're right, you can think in the Schrodinger picture, but let's just think in the Heisenberg picture. This is the state, and then we look at some correlators. So, on top of the state, we measure some correlators. One way to say it is, in the thermofield double state, you measure some correlators, like psi x1, psi x2 in the interior. And these correlators are different depending on whether or not you acted with a unitary on the left, if these points are inside the horizon. But you could also think in the Schrodinger picture. I don't know, maybe I didn't answer your question. Go, so you can ask, yeah.
Well, it was more or less that I thought the entanglement, because you defined the entanglement around the t equals 0 slice, that that there would have been some interaction there, but yeah, I think this is my misunderstanding.
Yeah. I mean, the entanglement was defined. I mean, here in the Heisenberg picture, the entanglement is just defined. We will actually talk a little bit about time-evolved versions of the state. So you can think of states where even in the Heisenberg picture, you can take a state and you can just evolve it with time, right? You get a different state. That's a distinct state, and so we are now actually going to talk about those states. So maybe you can ask the question again after we have this discussion.
Yeah, I will.
Great. Okay, great.
Can I ask another question about this?
Yeah, sure. Yeah.
I was just confused by one thing. The fact that the observer and the shockwave can meet in bulk does not contradict the fact that the two CFTs cannot affect each other by acting with white entirely one system, because that kind of correlator that you wrote down where x1 and x2 are inside the bulk is not a well-defined object from the point of view of the CFT, right?
No, it might be a well-defined object, except you might have said that phi is a combination of both left and right variables inside the horizon. So the degrees of freedom inside the horizon, you would have said, are comprised of degrees of freedom from the right and the left CFT. And so, we'll discuss now whether it's well-defined or not, but it's certainly true if you just take like phi to be a right CFT correlator, then it's not affected by anything, any unitary on the left. But what you would say is that the degrees of freedom in this forward wedge are combinations of degrees of freedom that come from here and here. So this phi is not like a purely right operator. It's left plus right operator, and that's how you would have usually explained this. I mean, we'll now describe some other paradoxes which maybe tie up to this. But before these paradoxes were discovered, this is what you would have said. You would have said this field inside is not actually only a right operator; it's a left plus a right operator, and that's why it's affected by what happens in UL. So this itself is not a paradox. It's just a curious property of how the bulk is kind of a little different from the boundary.
Perfect, thank you.
Okay, great. So now, I'm almost done. So let me just write down what the paradox is going to be, and we will stop here. So we are going to find that the following three are inconsistent. Okay, following three assumptions. In fact, it's related to some of the questions. Are inconsistent. So one, that the eternal black hole is dual to the thermofield double state, which we would certainly like. Right? Is dual to the thermofield state. So we would like this to be true, right? This is something which we've checked and we think is very well established. Second, that the same operators describe the interior or describe degrees of freedom in the interior in the thermofield state and in states which are related to the thermofield state by time evolution. And I'll explain what these are next time. So these are operators where you take the thermofield state. These are states of this kind. And you can perfectly well consider states of this kind. You can take the state and you can act on it with the left and the right Hamiltonian. And this is like just taking a Cauchy slice in the bulk and evolving it into the future. And you can consider such states. And such states actually also correspond to an eternal black hole, where you've kind of changed the entanglement between the left and the right a little bit. But in fact, the bulk geometry is exactly the same, as we'll discuss next time. And so you can ask questions about what are the operators that describe the interior of the black hole in these time evolved states. And the paradox is going to be that, let's say, assume that it's the same operators in all of these states. So it's going to be this. And the third assumption is going to be that disentangled states. So disentangled states, like just energy eigenstates, do not have a wormhole. Okay. So it looks like all of these are very reasonable assumptions. This is the assumption of state independence, except now we are not even talking about all microstates in the Hilbert space. We're talking about a very special class of microstates in the Hilbert space. We're talking about microstates of some one parameter family of microstates in the Hilbert space, and we are only asking that we have some operators that are state independent, in that the same operators describe the degrees of freedom in this one parameter family of microstates. Here is the basic duality, so it seems like a pretty innocuous assumption, and this seems like a pretty innocuous assumption, right? If you don't even have entanglement, then we shouldn't have a wormhole. If we don't have entanglement and even then we had a wormhole, then that would really be in contradiction with many things. If you don't have if there are two systems which are just not entangled, you can just separate them and do whatever you like on one system and something else on the other system, and you don't expect to see a wormhole. And so all these three look like they are very innocuous assumptions, but as I'll describe tomorrow, they will lead us to a paradox very much like the paradox that we found. But I'm out of time actually, so I will stop here and we will come to this paradox tomorrow. But the main point I'd like to emphasize and the main takeaway is that it's important that, it's not that these paradoxes that I described only work for the large single-sided black hole. Even for this very well understood system, we are going to end up in trouble tomorrow. So I will stop here and we can take a few more questions if there are questions. Now, maybe there are no questions today, or
let me try and ask one. So
okay.
the conclusion to the negative occupancy paradox that we found, the fact that it was used to argue either one of those two possibilities. In particular, why can I use that to argue that AdS CFT does not describe the interior of large black holes?
Yeah, so you could use, I'll describe a different resolution which will involve relaxing this assumption of state independence. But if you take these assumptions, then yeah, if these operators A tilde don't exist in the CFT, if somehow you need to if you just cannot describe the interior, then the whole paradox is not there, right? Because this paradox involves taking these operators and putting them inside a trace and then using some commutators and so on. But if these operators just don't exist in the CFT, like if the AdS CFT doesn't describe the interior and you need to supplement the CFT with some additional degrees of freedom before you can make sense of these operators, then the paradox would not arise. So, if these operators exist and there are some well-defined operators in the theory, then you run into this paradox. But if somehow, the theory just cannot describe the interior without having additional degrees of freedom, or somehow you need to, add some degrees of freedom to make the theory consistent, then maybe, you would get rid of this paradox. For instance, someone would say that you always have to couple the CFT to a bath. Okay? So you can never talk about black holes which are large black holes which never evaporate. You always have to take black holes which do evaporate. Then this paradox would go away, because now you would never have these typical states. You would never have these black holes which are dominating the ensemble. Now, no one actually says that, but someone could say that, and then the paradox would go away. So if somehow you always have to, you can only in some way think of evaporating black holes or atypical black holes, the paradox would go away. But maybe you don't have to do something so drastic. Maybe you can add a smaller number of degrees of freedom, and that will already be enough to get rid of the paradox. So if you don't, if AdS CFT doesn't describe the interior, then in a sense the paradox doesn't arise at all.
Okay, thank you.
Yeah, I want to emphasize that we will. It's not that we're going to end up with this one of these two conclusions. We will add, of course, a third one, which is that, we use state-dependent operators, and we'll discuss some pros and cons of that. But I just wanted to frame the paradox as it was originally framed, and the purpose of framing the paradox. So the paradox was originally framed to make one of these two arguments. So we'll describe a third one, but we'll also describe some puzzles with state dependence. And so if we don't like state dependent operators, then as far as I know, we end up with one of these two possibilities.
Okay, thanks.
Great. Any questions?
Yeah, I'm just wondering, because for the eternal black hole and the one-sided black hole, if we look from let's say just one CFT, then they are completely identical, right?
From one side, yes.
Yeah. Okay. So is this also the way we are gonna discuss paradoxes tomorrow? Or?
sorry. Actually, I should correct that. They're completely identical from the point of view of the metric and for coarse grain measurements. If you just look at a black hole, they're identical to the extent that pure states look like thermal states. So of course, if you make like very fine grain measurements, then in the single-sided black hole, you're in a pure state. So if you measure like all correlators on one CFT and you measure them to exponential accuracy, you will know that you're in a pure state. So if you measure the entanglement entropy, you get 0. But for the thermofield state, you really are in a mixed state. So the density matrix on one side is really e to the minus beta h. It's not a pure density matrix. So it's true that the black hole kind of looks the same if you look at it from a coarse grain point of view, and that the metric looks the same at late times. But the fine grain state is different, of course, between the eternal black hole and the CFT. So that's not how we're going to get the paradox. We're actually going to use this. But in any case, the way we're going to get the paradox is we're going to use this fact that this question we had about time evolution. So we're going to say that if the eternal black hole really is eternal, then you should have the same operators at all times. So we'll consider like observers who jump in at different times, and we'll ask for their experience. And if the eternal black hole, it really is eternal, then there's no origin of time. And so you should be able to consider observers who just jump in at any time. And we'll find that already is enough to lead us to a paradox. If you demand that observers who jump in at arbitrary times have the same experience, which you should expect because there's no origin of time, this really is an eternal black hole, then we'll end up with a paradox. We will end up, we will use the single-sided paradoxes, but we will first use this lack of the origin of time to reduce the eternal black hole to like a single-sided case, and then we'll just say the same words we had for the single-sided black hole. But we won't, we're not quite using the fact that at a coarse grain level, the black holes look the same. So the paradox will be like more intricate than that.
So a bulk observer wouldn't know whether he's in a single-sided or a two-sided black hole.
So when you say bulk observer, you mean a bulk observer who can only make like coarse grain measurements?
Yeah, yeah. I don't know how we would access the fine-grained.
You could, right? If you go like asymptotically far away, then you can frame things in the bulk. So as we said, I think there's sometimes people have this attitude that you should only talk about like fine-grained things. The moment you talk about fine-grained things, you should give up the bulk as a description, but I don't think that's necessarily the case. If you go to asymptotic infinity, there's a theory of quantum gravity you should be able to phrase, and in asymptotic infinity, in the theory of quantum gravity, if you're far enough, you should be able to ask questions about correlators to arbitrary precision. When we talked about flat space and we talked about the holography of information and many other things, we said if you go to asymptotia, you can then ask questions even in the bulk. And so you probably can ask these questions in the bulk. So when we say all the information is available in the boundary of a Cauchy slice, we're saying that you should be allowed to make measurements to arbitrary accuracy far away. So you could ask the questions, but you're right that if you take bulk observer to mean like a coarse grain bulk observer who just measures like the metric and a few other degrees of freedom, then such an observer would indeed not be able to see the difference between the two. But bulk observer who did something more would be able to see the difference between the two. Something more meaning would have to do very fine grained measurements, but a bulk observer who did do very fine grained measurements would be able to see the difference between the two states.
Okay, thanks. Yeah, but I was just because I don't. Maybe this is related to my previous question, but I'm not entirely sure how we should think of the black hole interior in the two-sided case now. Because
yeah, go on. Yeah.
Because sorry, I think that these are then because I know from if we would describe the RT surface of a whole CFT, then we would view it as a black hole horizon, then, right?
In the eternal black hole, yes, in the eternal black hole, the RT surface of one side would be the horizon, right? And in the pure state, it would, right, you just get 0. So you'd find some surface that shrinks down to 0, right? And that has to do with imposing this homology constraint. It has to do with the fact that, in one case, the homology constraint, in one case, the black hole formed from collapse. And so people say the homology constraint allows you a surface which just shrinks down to 0. Whereas in the other case, the horizon has always existed, and so you can't do that. So actually, these are not very good answers, but they're kind of invented to make sure that the entanglement entropy prescription gives you the right answer. It gives you area in one case and gives you 0 in the other case, which is what you would like. But we know that's the right answer. Leaving aside the holographic area prescription, we know that in one case it is a thermal entropy, and in the other case it is 0. So that's the sense in which these are different. But as far as describing the interior goes, people used to think that for the eternal black hole, it's simple to describe the interior, because they would say this. They would say, you think of degrees of freedom here, like somewhere here, and they just describe by degrees of freedom that come from here and from here. So the difficulty always was, how do you describe the interior of a single-sided black hole? Because in a single-sided black hole, you don't have like this left boundary. So the earlier idea was that if you don't have the left boundary, so in a single-sided black hole, you want to ask where are the degrees of freedom that come from here, and so one has to do some work to do that. But for an eternal black hole, people used to think that it's clear, you just write down a linear combination of these degrees of freedom, and that describes the interior. But as we will describe tomorrow, that's not so straightforward.
Yeah, I think my confusion is clarified now. Thanks.
Okay.